Yes.
Right. So before we get into the core topic of astrophysics, let us understand the terminology that we frequently use on our day-to-day life, and we use interchangeably, thinking that they all means the same, that are astronomy, astrology, and astrophysics. Astronomy is basically, just study of stars just to predict what is going to happen with us. It is just, by looking at the position of the stars, planets, and moon and the sun, we predict what is going to happen the next day, right? That is something called astrology, right? We know astrologists are there who look at our hand or look at some our name and understand with a zodiac sign, predict what is going to happen with us and what is our fate. Whereas astronomy is just looking at the stars. You go night sky, look at the sky with your bare eyes without telescope, nothing. It's an astronomy. Just looking at sky is an astronomy. But yes, a better astronomy, you having a telescope, you look at the stars which are very far away from you, and want to know how far they are, what is their age, what is their temperature, all that you are interested, you're curious to know, is an astronomy. And the tools that you use to know these things, such as the math you use to know how far the star is, the math you use to know how hot a star is, math you use to find out the components the star is made up of. That's basically the astrophysics. So astrophysics is just the usage of physics concepts and mathematical tools to understand quantitatively about few things. That's astrophysics. Okay. So basically what we're doing in this chapter is astrophysics because not just going to understand what planet is, what star is, what satellite is, but also we're going to understand beyond that. We're going to understand how far a planet is or how far a star is, what is the temperature of the star, what is the age of a star, all that. So we're doing astrophysics in this chapter. Okay. So everything starts from the dust, right? Maybe, like you talk about the star formation, you talk about the planet formation, you talk about asteroid formation, you talk about the comet formation, anything that you see in space. Everything started from dust, right? And we call that dust as nebula. And the plural form of nebula is nebulae. So what is a nebula? It is derived from the Latin word cloud. Nebula are clouds of gas and or dust in space. Nebula forms from the dust and the gas of the Big Bang and the death of the stars, right? I mean, the we know that the Big Bang is the event where the universe originated. The dust that still there from the event of the Big Bang, and there is some dust which must have formed from the death of the existing star. Maybe after 1 million year, our sun will explode due to an inequilibrium state, right? Maybe the sun will run out of the fuel. All that reason may cause the sun to get unstable and the sun may explode. So the dust which is going to release out of the sun will consider to be the nebula, and maybe that dust will lead to form future planets. So nebula emits their own light or reflects nearby massive star, right? I mean, you look at the sky, you see some bright light spread across the sky, which may looks like a cloud. They're basically nebula. They're just dust. Why they're emitting light? One, they might be emitting light of their own, but also sometimes they emit the light of the star nearby, which are very massive. So Orion Nebula is situated in the Milky Way galaxy. It is one of the brightest nebula and it is visible to the naked eye in the night sky. I mean, this is one of the nebula which you can see without the use of the telescope nor the use of a binocular. You can see with your naked eye. How to locate it? Simple. You just first find the Orient belt. That's the Orion belt, three giant stars. I mean, not giant stars, the bright stars in our night sky. Very easy to locate them. They're the three, like a friend sitting next to each other always. You locate them first, and right below them, you'll find a bright cloud, which is basically a nebula called as Orion Nebula. Next, what does nebula do? As we said, nebula is the dust that is going to form planet or moon or star or asteroid or comet in future, right? So nebula is the beginning point of it. So what is a planet? So there are more planets than stars in our galaxy. But what do we mean by planet? Something that is revolving around the star is called planet. Okay, anything that is revolving around the stars are called as planet. Example, Earth revolves around the sun. That's why Earth is called as planet. Mercury, Venus, Earth, Mars, all these are planet. So current we have 8 planet. We used to have something called Pluto, but now it is considered as dwarf planet. So what is a criteria or eligibility for something to be called as a planet? I mean, why Pluto was called as planet earlier, but now no more called as planet? That means there must be some criteria for anything to be called as a planet. The criteria are, first, it must orbit a star. It must be big enough to have enough gravity to force into spherical shape. It must clear the neighborhood around its orbit. So yes, Pluto is orbiting the star. Yes, Pluto is having enough gravity to form a spherical shape. But yes, Pluto is not big enough to clear the neighborhood around its orbit. For example, Pluto is basically a part of an asteroid belt. Okay, we have asteroid belt between Earth and Mars. Sorry, between Mars, Earth, Mercury, Venus, Earth, Mars, Jupiter. Yeah. So there is a belt between Mars and Jupiter. We call it as asteroid belt. And we have another belt called KPO, Kuiper Belt, beyond the Pluto. So when scientists observed the Pluto with the telescope, they found that Pluto is as same size as those asteroids. So why did we consider Pluto as a planet then? If we consider Pluto as a planet, then all the asteroids revolving around the sun, along with the Pluto, must be considered as planet. So that means no, Pluto doesn't have enough strength, enough mass to clear its neighbor. Means if any asteroid come and hit the Pluto, Pluto will be easily taken out of its orbit. But you know that if any asteroid come and hit the Earth, I mean, Earth will be able to bear that collision and will withstand and will not go out of the orbit easily. I mean, yes, with a very big asteroid, it's a different story, but I'm talking about small scale asteroids. It will not be able to throw Earth out of its orbit because Earth has enough mass to withstand that collision, but Pluto doesn't have it. And that's why Pluto considered as a dwarf planet and no longer is a planet. Let's talk about moon. What is a moon? Something that revolves around a planet is called a natural satellite. And there is a natural satellite revolving around the Earth. We call it as a moon, right? So, what is the importance of the moon around the planet Earth? There's a huge importance. And the importance is that it stabilizes our planet's wobble and that help us to stabilize our climate. Just imagine that the planet is wobbling, not just revolving, not just rotating, but also wobbling. And that wobbling will cause the Earth to have a random atmosphere, I mean, random climate, random weather. I mean, today you see that we have summer in India, Australia may have winter, and it will be there for another 3 months or 4 months. And after that, there will be rainy season, then there will be a winter season. So there is a perfect pattern for a weather. It's just because the Earth is rotating in a fixed orbit. Also, Earth is rotating in its own axis in a fixed orbit, tilted at an angle of around 21 degrees. But if Earth wobble, then Earth will not have a constant climate, right? And fortunately, we have moon around us, which doesn't allow the planet Earth to wobble. That's why we say that the moon presence helps stabilize our planet's wobble, which helps stabilize our climate. Let's learn more about moon. That moon has a very thin atmosphere called exosphere, and the entire surface is cratered and pitted from the impact. Because Earth Moon has a very small atmosphere, very thin atmosphere. That is why easily all the asteroids, even a small size asteroids, they all can easily penetrate through this thin atmosphere and go and hit the surface. And that cause all that crater and the pitted, right?
Hmm.
And
Wait,
what does moon, yeah,
how does the moon stabilize the climate?
right? And just think about you holding hand of a child. So child wants to go away, but you don't let because you're holding it. So that's the gravitational lock between moon and earth does not let earth to wobble. Clear?
Oh, okay. Hmm.
Right. So what does moon do addition to this gravitational lock? Earth has tides because of the moon. Because what happens is the earth is covered with 70% of the water, we know about that. And when moon is closer to the earth, any part of the area where moon is closer, for example, let me draw it on the board. If this is earth and this is the section where the moon is, so the that because of that closest r- being the closest position to the earth, the water gets pulled up by the moon like that. But yes, it will never go till moon because earth says, wait, I'm also having a gravitational force on you. How can you go away from me? So that pull of the moon on the water causes the tide to rise up, and the pull of the earth causes the tides to fall down. So, anyways, the cause of the tide is the moon because moon pulls the water towards it. It orbits the Earth with a time period of 27.3 days. This is the time period taken by the moon to complete one rotation around the Earth. And one thing to be noted down that we always see the same side of the moon, no matter wherever you are. If you are here on the Earth, if you see this side of the moon, forever in your life, you'll see the same side of the moon. Why, sir? Because as I said, moon and Earth is gravitationally locked. So moon is just revolving around the Earth, having the same space facing towards. If if I have to draw more precisely, a better diagram, then I should draw something like this. If this is moon, Earth, and that's moon, if I'm saying this side is A, if the moon goes there, that side A comes here. If the moon goes there, the side A comes here. So you can see the side A is always facing towards the Earth. And that's what due to the gravitational lock between the Earth and the moon. That doesn't let moon to wobble, nor it lets Earth to wobble. Okay, so this is how the moon changes its position with the earth, and that causes the different phases of the moon. For example, if the moon is here, sun rays are coming, all the sun rays reflect back, no rays from the moon comes to earth, and you see nothing. I mean, you see what? You see a black region of the moon, right? You see the moon to be like this. We call that moon as a new moon, right? People were in this position, right, over the tip of the earth. For them, it is a solar eclipse because moon comes exactly in between the sun and the earth. For the people in this region, they'll see, I mean, they see the darkness for some time until the moon goes away between the earth and the sun. So that shadow which is casted by the moon on the earth is what leads to dark region here. Let me call the region as A. And we call this event as a solar eclipse or total solar eclipse, right? Next, what if the moon comes on the other side? That means Earth is now in the between sun and moon. Now, Earth between sun and moon means this time Earth will cast shadow on the moon, and that casting the shadow on the moon caused the moon to appear like a red giant. And that event is called as lunar eclipse. And sir, why is it red giant? Isn't when moon is cast, even when Earth is casting a shadow on the moon, isn't the moon should have appeared like dark moon? a black moon, but not any other color. But why red? And there a reason behind this is called diffraction. What happens is when the light travels around the Earth, it bends around the Earth and reaches the moon. And the phenomena of light bending around the obstacle is called as diffraction. Now, why only red reaches? Why not like out of V, I, B, G, Y, O, R? Why only that shorter wavelength reaches? Why not larger wavelength like red, orange, all that reaches moon? The reason is, I'm sorry, why only larger wavelength like red, orange reaches moon? Why not this shorter wavelengths like violet, indigo, blue, green reaches moon? The reason is we learned under diffraction that larger the wavelength, larger the diffraction of the wave. I mean to say, if I'm sending out the wave through a small slit, so you can see this is a wavelength lambda 1 and this is wavelength lambda 2. From the diagram, we understand that the lambda 2 is larger than lambda 1. So which will cause more diffraction when passed through the slit. So lambda 1 causes this much diffraction. Lambda 2 will cause this much diffraction. So you can see larger the wavelength, larger the diffraction. So that is why the red easily diffract around the earth and reaches the moon. Whereas violet, indigo, blue and all being the shorter wavelength doesn't diffract much and doesn't reach the moon. So I'll show you an image of a full moon, a lunar eclipse that is going to happen very soon. Let me show you lunar eclipse that is going to happen very soon. Yeah, that's how the moon appears during the lunar eclipse when the Earth casts shadow on the moon.
Mm.
As soon as the Earth stops casting shadow on the moon, then moon will start appearing whitish in color, having all VIB, GY were reaching it. But until the moon is casting shadow, the moon appears to be red giant. And we call that moon as a blood moon actually. And if you want to read at what time it is coming, I think it is coming. Although the moon
And
has its reputation for stealing all the glory night this March, it is set to become a tad bit more striking. So, yeah,
yeah,
on the
this
9th,
happened I think 2 days ago.
exactly, 13th and 14th, North America, South America will get a great view of this all phase of blood moon. I'm sure you must have seen this, right?
I didn't see it, but I did hear about it.
Great. I mean, at least you heard about it, right? Maybe you can see some online videos. Someone must have captured it, and you must see that, right? Anyway, so
Mm-hmm.
you understand this. This is called basically the phases of the moon that decides by the position of the moon, sun, and earth. So more about this. So that's how the solar eclipse happens when moon comes in between earth and sun. And if earth comes between sun and moon, that's how the lunar eclipse happens. So there are a few famous sites where either human have landed or some satellites have landed. Those are few sites like this, and were very popular uh, site landing of the human. Right? We talk about Neil Armstrong or Yuri Gagarin being the first man to land on the moon. So those are the footprints and the flag they hosted on the moon. Whereas there are a few other landing sites of human, such as Apollo 15, Apollo 17, Apollo 11, Apollo 16, and so on. In addition to that, we have few robotic landing sites. These are the few robotic landing sites. And geographically, there is a big lava tube pit over here. And that's the big crater, which we see, which we can easily see with the powerful binoculars. Now, we'll talk about stars. The very important topic under E5 about stars, about their evolution, all that. So, yes, stars are also formed from the cloud that we discussed about earlier, called nebula. So when those dust particles come closer and slowly to form solid mass, they get collapsed under its own gravitational attraction, right? And slowly that material, when these materials are coming closer and closer, they are packing, they're becoming a solid structure due to that gravitational collapse. They're having a tremendous amount of heat produced due to that collapse, and it starts to shine. So all that heat, which is causing the this solid mass to shine, we call this solid mass as a protostar. I mean, it is no longer a star which is producing light or heat due to fusion reaction. No longer hydrogen is under fusion. This entire heat is produced due to that material, which is coming closer and closer, packing closer and closer, due to that compression, due to that collapse. All that collision of the particles is producing the heat. Now, it is this core at the heart of the collapsing cloud that will one day become a star, right? One day become a star means one day it will have enough mass to start fusion reaction. But for now, it doesn't have enough mass. So we call this as a protostar. So we'll see the sequence of the star or the stages of the star. So it starts with nebula. Now, how much mass the nebula has, how big the nebula was, decides the fate of the star. Means, will it die as a white dwarf, or will it die as a neutron star, or will it die as a black hole? Finally, maybe 1 million billion years later, it will be decided by the the original mass of the nebula. If the nebula was small, then it will form either a low mass star or a medium mass star. So even Sun is an example of a medium mass star. If the nebula is very large, it will form a high mass star. Okay. So whatever, the nebula first form main sequence star and then form red giant star. Then under instability, under instability, it explodes either as a planetary nebula or explodes as a supernova. An explosion may form a white dwarf or a neutron star or a black hole. So we'll see that stages one by one. Let's start. So what are the types of stars we have? First, we have protostar. A protostar is what you have before a star forms. I told you that this is the time where the heat is produced by that collapsing of the material due to the gravitational force. It is a collection of gas that has collapsed down from a giant nebula. This phase of the stellar evolution lasts about 100,000 years. Over time, gravity and pressure increases, forcing the protostar to collapse down. All of the energy release is from heating caused by the gravitational energy. No longer it is producing heat due to the fusion. All the heat is produced due to that gravitational energy. All that collapse of the material towards the center. Nuclear fusion reactions haven't started yet, as I said earlier. Now, T-Taurus star. This phase occurs at the end of the protostar. I mean, you can consider it to be an end of the protostar or a beginning of what? Fusion reaction. So gravitational pressure holding the star together is the source of all the energy. No longer a fusion started yet. They resemble the main sequence star. I mean, this is the beginning of the main sequence star. The star will remain in the T-Taurus stage for about 100 million years. Next comes the main sequence star. Main sequence stars can vary in size, mass, and brightness, decided by the nebula. They convert hydrogen into helium in their cores, releasing a tremendous amount of energy. So obviously, if you want hydrogen and hydrogen to fuse together, you need enough mass. If that star has enough mass, then star will start to involve hydrogen into fusion. And as soon as hydrogen starts to involve into fusion, it becomes the source of that energy which is released, which makes the stars to emit out the radiation outward in the form of light or heat. They are in a state of hydrostatic equilibrium. What is hydrostatic equilibrium? Let's see this example. So say you have a pressure cooker. Okay, you have a pressure cooker on a stove. So you know that when you're boiling the vegetable, having a water inside, there's a vegetables, you're boiling them, carrots, all that you're boiling them in the water. So pressure cooker is happily helping you to boil the vegetable. If I ask you what is the state of the pressure cooker, you'll say it's a stable state. Why? Because the pressure cooker is not exploding outward, because the pressure exerted by the steam in the outward direction is cancelled by the pressure exerted by the pressure cooker inward, right? If I ask you if this is the pressure cooker, who is exerting the pressure outward? It is the steam exerting the pressure outward. Then who is exerting the pressure inward? It is obviously pressure from the atmosphere outside, plus pressure by your aluminium body. Aluminium body is also exerting pressure inward. If in case, imagine the pressure outward is larger than the pressure inward, then what will happen? The pressure cooker will explode. Or if the pressure from the outside is larger than the pressure from the inside, then the pressure cooker will implode, right? So either explode or implode is due to imbalance in the pressures. And if the pressures are balanced, we consider that state as hydrostatic equilibrium. So this was just an analogy for you to understand what is meant by hydrostatic equilibrium. Now let's talk about star. So what is the pressure inward in the star? It is a gravitational pressure. You know, the gravitational pressure is always towards the center, tries to bring all the material of the star, that is a gas or dust, everything on the star surface, towards the center. And the fusion is causing the outward pressure. We call thermal pressure, right? Fusion wants the expansion of the gas. Fusion wants the material to expand in the outward direction. So, if this is the star, what is the pressure in the outward direction? It is the thermal pressure in the outward direction. What is the pressure in the inward direction? It is the gravitational pressure in the inward direction. If your gravitational pressure is equal to thermal pressure, we say that condition as hydrostatic equilibrium. If anything is less, for example, what if the gravitational pressure is higher than the thermal pressure? Then the star will implode. What if the thermal pressure is higher than the gravitational pressure? Then the star will explode. Then we say that the star is not in hydrostatic equilibrium, right? So, is star in hydrostatic equilibrium when it is in a main sequence stage? The answer is yes. So, continue. So, gravity is pulling the star inward, and the pressure from all the fusion reactions are pushing outward. The inward and outward forces balance one another out, and the star maintains a spherical shape. The minimum amount of gravitational pressure you need to ignite the fusion in the core is 0.08 times the mass of the sun. And this criteria is needed. If a star does not meet this criteria, then it never forms a main sequence star. It dies as a T-Tauri star. So what happens? Slowly, a star is running its fuel on hydrogen. Slowly, the hydrogen fuels run out, and then it starts to involve heavier fuels such as helium. And obviously, when the star has enough ability to involve helium, then helium will start involving. And if helium is also running out, then iron, helium, lithium, then lithium will start to form into fusion. Later, oxygen may start form into fusion, or carbon also may start form into fusion.
I don't,
And it depends
I
on,
don't,
yeah,
I don't understand the process of like from it going from having hydrogen to helium.
because what is happening fusion when hydrogen and hydrogen fuse together? Let me write down the equation. What does a fusion actually means? So when hydrogen 1 1 reacts with another hydrogen 1 1, it forms hydrogen 1 2 plus one positron. You can see the equation is balanced on both sides. Plus tremendous amount of energy, no doubt about that. Now this hydrogen 1 2 fuse with another hydrogen 1 1 to form helium 2 3 plus energy. This helium 2 3 fuse with another hydrogen 1 1 to form helium 2 4 by releasing a positron plus energy. So basically, how many hydrogens are fused together to form a stable version of helium? One, two, three, and four. So I can write a short equation that four hydrogen, when fused together, right? I mean, let me erase this part.
Yeah. When four hydrogens, 1 1, fuse together, it forms one helium 2 4 plus total of two positrons are released in this reaction, positron 1, positron 2, plus tremendous amount of energy. So that's the fusion reaction of hydrogen. And slowly, when all hydrogens are over on surface, then what is left over now is helium's left over. Now helium will start fusing like helium 2 4 with another helium 2 4, and the reaction occurs. I'm not interested to talk about future reactions. But yes, that's how the fusion reactions takes place. Clear?
Yeah.
Perfect. Now, as I said, how many, what, until what the fuel involves, until what heavier fuel involves, like whether hydrogen will be the last fuel used by the star, or helium will also be involved, or even heavier elements like such as carbon will involve. It all depends on the mass of the star, right? I mean, if it is a very massive star, then carbon can also be act as a fuel. But a low massive star, maybe helium is the last fuel it can use. I mean, I'm not saying the carbon is not formed, but it has no ability to involve carbon into fusion reaction because carbon needs more energy than the hydrogen fusion requirement. So therefore, if the star doesn't have enough mass, the carbon will not be involved into fusion reaction. So that means the age of a star depends on the mass of the star. That's what I was talking about, that how the fate of the star is decided by the mass of the star. Right? So let's continue. So after main sequence star, we form red giant star. When a star has consumed its stock of hydrogen in its core, a shell of hydrogen around the core ignites, continuing the life of the star. So all the hydrogen in the core is used up. Now what you're left with is a shell around the core, like last thin layer around the core is left over, which is igniting, continuing the life of the star. The helium and even heavier elements can be consumed in fusion reactions. It can be 100 times larger than it was in the main sequence phase. The red giant phase of a star life will only last few 100 million years before it runs out of fuel completely and becomes a white dwarf. So yes, so what is happening? Why does it become a red giant? Why do we call red giant? Why didn't we just call it red? The reason we call it red giant is because if this is the core, which is fused, like the core is a solid structure, right? It doesn't change its shape. But the outer thin layer, which is like gaseous material, when they starts to heat up, that gas starts to expand and go away from the core. And that is what makes the star to appear bigger and bigger. That's why we say the star has now become very giant. So understood the meaning of giant. But why red? Because when the star is running out of fuel, right? It starts running out of fuel. It now starts to cool down. And when it starts to cool down, and it is now still in a red stage. I mean, you know that in the VIBGYOR, the initial it is a red or orangish in color, but if star continues to burn with fuel such as helium or carbon and continues to heat up more and more, then slowly in future it will become a blue star. We call it as blue giant star. But that depends on the mass of the star. I mean, whether the sun has enough ability to involve the fuel to turn into blue star in future depends on the mass. That's a different story altogether. But I'm talking about not the future. I'm talking about right now. How is it? It is red because it's running so hot, because it is burning all the fuel. Obviously, it is red. In future, it may turn into blue. But why it is giant? Because all the gases, the top layer has gone so away from the star core due to that heat. You know that temperature when rises up, the gas expands. So all the gas that goes out makes the stars to appear very big, very giant. That's why we call it as red giant. But yes, as I said in the last statement, the red giant phase of the star life will only last few 100 million years before it runs out of the fuel completely and becomes a white dwarf. So what is a white dwarf? So when a star has completely run off hydrogen fuel in its core and it lacks the mass to force higher elements into fusion reaction, it becomes a white dwarf star. So what happens is that the core is running out of the fuel. Now it has a carbon, it has a heavier elements like oxygen, but the star doesn't have enough mass and it lacks the mass to force higher elements into fusion reaction, what happens is it is no longer able to ignite. That means no longer thermal pressure will increase. So thermal pressure will start to reduce. But will your pressure reduce? No. Gravitational pressure is always constant because gravitational pressure depends on the mass of the core, right? It is constant all the time. So that means as soon as thermal pressure reduces, the gravitational pressure, which is inward pressure, dominates the outward pressure, allows the star to collapse immediately, leaving all that outer layer away, just left with the core. So all the outer layer just vanish outward because they have gone so far away from the core, they no longer has ability to come back. They just vanish, they just go out. So core is what left now, and we call the core as a white dwarf. So does the core glow or does the core completely turned off? I mean, does it appear to be dark? No, no, no. This white dwarf shine very brightly. Reason, once it was a hot star. Don't forget that. Once it was a main sequence star. Once it was a red giant star. So the core will continue to glow due to that heat until it cool down and reaches the temperature of the universe. Right? So let's continue. The outward pressure from the fusion reaction stops because no longer fusion happens, and the star collapses inward under its own gravity. And white dwarf shines because it was a hot star once. It will just cool down until it becomes the background temperature of the universe. This process will take hundred of billion of years. So no white dwarfs have actually cooled down yet because we know that the age of the universe is about 14 billion years, around 14 billion years. And any white dwarf takes about hundreds of billion years to cool down. That means no white dwarf have completely cooled down yet, right? And what happens? What about the big stars? What about the massive stars? I mean, sir, you discussed about a medium or small size star. It turns into red giant. What about massive stars? After main sequence, they turn into supergiant stars. I repeat once again. So from the nebula, you either form a small or medium giant star, I mean small or medium star, medium-sized star, or a giant star. A small medium-sized star turn into a red giant star, whereas a massive star turn into a super red giant star. So I'm talking about this now. We've done everything about a medium-sized stars. Now we are talking about massive stars. Okay, so let's look at that. So after the main sequence, it turns into supergiant star. What is the difference? The only difference is that it is a size. That's it. Otherwise, the process of red giant and super red giant is the same thing. So yeah, a largest star in the universe are supergiant stars. They are monstrous between a mass between 1.25 to 12 times the mass of the sun. They consume hydrogen fuel at an enormous rate and will consume all the fuel in the cores within just a few million years. Obviously, massive the star is, faster it uses the fuel. Smaller the star is, slower it uses the fuel. That is why we say giant stars live fast and die young. Why? Because it uses the fuel at an enormous rate and running out of the fuel very quickly. That's why we say just die young. Explodes as a supernova leads to either a neutron star or a black hole. So yes, because of being very big star, that inward gravitational collapse create a shock wave that that gets released across the universe, and that shock wave can be felt even millions of years, light years far away. Right? I mean, scientists keep observing some shocking shock waves are coming towards us. All those shock waves can also be due to a supernova explosion, very far away from us. And obviously, supernova explosions only happens for supergiant stars because medium-sized stars, they don't undergo supernova explosions because they do not have enough mass to cause that catastrophic explosion, right? That implosion of the star is what causes that supernova explosion only happens with the supergiant stars. Yes. So what happens after they implode as a supernova? They form either a neutron star or maybe a black hole. So let's talk about neutron star. If a star has between 1.35 and 2.1 times the mass of the sun, it does not form a white dwarf when it dies. Instead, the star dies in a catastrophic supernova explosion, and the remaining core becomes a neutron star. So, what happens is if the star is a medium sized star or a small sized star, the core remains as a white dwarf. Okay. But what if the star core is very big? That inward gravitational pressure causes all the electrons and all the protons to fuse together, which is a very strange event happens, right? It doesn't happen on Earth's surface. You never find an electron and proton to fuse together. But it happens only in the neutron star. Because when these electrons and protons come together, electron being negative charge, proton being a positive charge, when they come together, forms a particle with zero charge, and we call that particle as a neutron. That means if each and every electron and proton come together to form a neutron, that means the star will only have neutrons on its surface, will have nothing else. That's why it is called as neutron star. And when electron and proton has come closer, you understand that it is the densest particle forming. I mean, this entire star is not having any atoms anymore. Like you can't imagine an electron revolving and the proton is somewhere at the center. No, because electron has just got into the proton. So no more empty space. We know that atom is completely empty space. So there's no more empty space because there's no electron and proton staying separately. That is why I say that the neutron star is the most densest thing in the universe. We try to compare something like this. A one spoon of neutron material, I mean the star, whatever, one spoon of neutron star is about 100 Earth mass. You keep 100 Earth mass, it's equivalent to one spoon of neutron star. That dense a neutron star is. Okay. So, as its names implies, a neutron star is an unusual type of star that is composed entirely of neutrons. The intense gravity of the neutron star crushes proton and electron together to form neutrons. If stars are even more massive, so why not, sir? Neutrons are also fusing together. I mean, you told electron and proton fusing together to form a neutron. Why not neutron and neutron fusing together? Yes, it will happen if the star is more massive. And when the neutron and neutron starts to fuse together, all that is finally form a black hole instead of a neutron star. Clear? So that's all about the stages of the star. Let's talk about astronomical distances. So, yes, we don't talk about any distances in space in terms of kilometer or meter because they become a very small units. We need to use something which is better or easier to use for larger distances. And one of that is astronomical unit. So, one astronomical unit is the average distance between the Earth and the Sun, which is about 150 million kilometers, which is equal to consider as one astronomical unit. And the second unit for distance we use in astrophysics is light years. So a light year is nothing but a distance traveled by light in 1 year. How far a light has traveled in 1 year, that distance is equal to 1 light year. I mean, you want to find out how far it traveled in 1 light year? I mean, 1 year, you know the formula distance equals speed of the light multiplied by the time it traveled. And what is the speed of the light? 3 times 10 power of 8. And how long it traveled in 1 year? Obviously, 1 year is 365 days into 24 hours into 3,600 seconds. Whatever you finally get is equal to this much meters. And that's 1 light years in meters. And the third unit that we use is called parsec. So parsec is most commonly used unit. I'll talk about this parsec later. But now, only thing you need to know is that 1 parsec is 3.26 light year, which is about this much meters. So do I need to memorize all these conversions? No. Examiner will be providing that information, and your data booklet has some information about these. So you don't need to memorize any of these things. But yes, the examiner may ask you to calculate 1 light year is how much in meters, which is a very simple calculation. Distance equals speed into time. Simple, right? Next. Let's talk about a method to find the distance of the nearest stars. One of the method is called as stellar parallax. There are many, many, many methods. One of the method is called as stellar parallax. So what is this method? Let's understand. So we'll look at the nearby star from the Earth, say in the month of December, with the help of a telescope. And we know what angle we are forming here. Therefore, we know what angle is formed at the star. And we call that angle as a parallax angle denoted with the letter P. And after 6 months, the Earth goes to the other end of the sun, and again it observes that same star to just make sure the angle is same, or if it is slightly different, to take the average to avoid the error. We measure twice, one in the month of December, say, another in the month of June. So by knowing this parallax angle and knowing the distance between Earth and Sun, that is one of the side, let me call it as one astronomical unit, can we find this distance, the hypotenuse of this triangle, which is a right angle triangle? Yes, we can find out. Which, I mean, I can use what? Sine theta is equal to opposite side, which is one astronomical unit, divided by hypotenuse, distance d. So d will be one astronomical unit over sine theta. Since this theta over here is very small, this parallax angle is very small, and we know that when theta is very small, it can be replaced with theta in radians, right? When theta is in radians is very small, we can replace sine theta with theta. So one astronomical unit divided by theta in radians. So when you substitute theta in radians, sorry, theta is not in radians actually. The theta will be substituted in a unit called arc sec. When you substitute, numerator is obviously one astronomical unit. When theta is substituted in the unit arc sec, the final value that you get for the distance is called parsec. That unit is called parsec. I repeat, astronomical unit divided by arc sec is called as parsec. So by using this formula, if we calculate the distance, we get the distance in parsec. And you know the conversion between parsec to light year and light year to meters, you can get that. And we call this method as a stellar parallax. Okay, so yeah, I mean, one method is obviously by using a telescope, and the other method is by taking a photograph. We take photograph one today, and after 6 months, we get to know how far on the photograph the star has moved in terms of distance. Now, in terms of distance on the photograph, this much it has moved. How much it must have moved in reality, conversion we do, right? We scale up, right? We know how much on the photograph 1 centimeter is equal to. Then we measure how far the star has moved between the two photographs, and we calculate the actual distance of the star, which is called photographic method. But there's a problem with this method. The problem is the parallax angle is much smaller, very, very small angle actually. It is so small that it's very hard to measure that angle with the help of telescopes from the surface of the Earth. That is why we send telescope outside the atmosphere with the help of satellites such as Hubble Space Telescope, and recently we have James Webb Space Telescope, all that. Because it can give the accuracy of the angle to 0.001 arc sec. Whereas from the Earth, we have accuracy of 0.001 only to two decimal place. Whereas outside the surface, Earth's surface, we have a precision to until three decimal place. It is all because we don't have any scattering of light outside, or neither we have any turbulence due to the atmosphere causing the twinkling of the stars, right? Because outside the Earth's surface, Earth atmosphere, there's nothing that will cause disturbance to the viewing of the star. So that's about stellar parallax. Now let's talk about HR diagram. So what is a HR diagram? So HR diagram is basically a diagram that shows the spread of the stars across a graph based on their luminosity and their temperature. Means all the higher temperatures, let me use another ink, all the higher temperature stars on the left side, on the all the lower temperature stars on the right side. So next classification, all the higher I mean, all the brighter stars on the upper side, brighter stars on the upper side, and all the dimmer stars on the lower side. That means any star in this region, let me call it as A, is a higher temperature dimmer star. Whereas in the region B, lower temperature dimmer star, region C, lower temperature brighter star, or region D, higher temperature brighter star. So that is what HR diagram is all about. It shows the different stars at different positions based on the temperature and the luminosity, right? And when we place all of those stars in our space, we'll find there is a belt that is formed, and that belt is consist of all the main sequence star, and sun is over here. That means sun is with the luminosity of 1. So what does it mean 1? We talk about the luminosity in terms of sun's luminosity, remember that, okay? And we say 4 times the luminosity of the sun. We say 5 times the luminosity of the sun. That means what is the luminosity of the sun? Obviously 1 times the luminosity of the sun, no? That is 1 here. Relative, we talk about relative luminosity. Similarly, the sun temperature is about 4,000, 5,000, somewhere around that. That's why sun is sitting over there. Now, you know that supergiant stars are very, very high temperature stars. That's why they are on the upper side or on the right side. Sorry. They are bright stars, I meant to say. They're bright stars, that's why they're on the upper side. And we have blue stars, blue giant stars on the left side because higher temperature stars, whereas red giant stars on the right side because they're low temperature stars. What about white dwarf stars? They're very bright in sky because the core is glowing so brightly. But but sorry, they're very hot star, right? They're very, very hot star, but they're dim stars. I'm sorry. They're very hot star because once they were a red giant stars or they were blue giant stars.
I
But why
thought they
they
were the brightest though.
come again?
Door stars? I thought no, aren't they the brightest? Or like
No,
among
no,
the
no, no.
brightest?
When compared to the brightness of the blue giant stars, they're less brighter, no? Why? Because blue giant stars are very massive stars. Blue giant stars are the one that form the neutron star. They will not form white dwarf, no. Medium giant, like I'll tell you the stage. Like let's talk about the sun, how it goes. Sun will form a supergiant star. Giant star. It will form a giant star, and slowly it will turn into a blue star in future, and it will form a white dwarf like that. That's going to be the phase of the sun. You saw that
Okay.
stages, yeah. So that's it. That's about HR diagram. But I have a beautiful video to show. Let me show this video. Tell me if you're able to hear the audio or not. Audio is there?
No, I can't hear it.
Now you will able to hear it.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot, but even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
So the last topic that we have is Chandrasekhar limit and OV limit. So what is Chandrasekhar limits? Chandrasekhar limit help us understand that which star will turn into a white dwarf star. It's basically a limit for the white dwarf. The Chandrasekhar limit stipulates that it is impossible for a white dwarf to have a mass of more than 1.4 times the mass of the sun. It sets the higher limit for the stellar mass, beyond which it will not form a white dwarf. It will form either a neutron or a black hole. So that means it is a higher limit. What Chandrasekhar limit sets? It sets the higher limit to form a white dwarf. Whereas a Walk-off limit, also known as Oppenheimer Walk-off limit, in short OV limit, places an upper value on a neutron star for which a neutron degeneracy is able to resist further collapse into a black hole. This value is 3 times the solar mass. So OV limit sets the higher limit for the neutron star. Means if any star is 3 times the solar mass, any neutron star is 3 times the solar mass or higher, then only it will form a black hole. Lower than that, it will form a neutron star because a neutron and neutron can never come closer due to a pressure between them called neutron degeneracy pressure, which always resists further collapse. But if star mass is higher than 3 times the solar mass, then the neutron degeneracy pressure cannot resist further collapse into a black hole. So these two limits, Chandrasekhar limit and OV limit, sets the higher limit. Please remember, Chandrasekhar limit sets the higher limit for the white dwarf, whereas the OV limit sets the higher limit for a neutron star. So that's all the unit E5 is.